Okay guys, welcome back to my channel. In today's video, I'm going to be going over some practice problems for Reynolds Transport Theorem. So let's get into it. If you remember the general form of Reynolds Transport Theorem, or actually this is the mass conservation form of it, I'm going to be showing you guys. Oops, sorry. So this is going to be our property that's coming in, out. In this case, we're going to be looking at mass flow rate. This is going to be our control volume, so our storage and our transport. Yeah, so let's go ahead and see what we can do here. So in this problem, or in most problems, when you use Reynolds Transport Theorem, you want to make your control volume. That's your fixed area in space where you have your like your flow in and out. So let's take a look at this problem. Consider the steady flow in a water pipe to an addition. So if you actually look down here, they give us the equation to use, and how they got that equation is because we have steady flow, and so we have steady flow, which means that we can literally just take this term out. Now we're only working with the inlets to outlets, and so we have this mass flow rate, and since we're just dealing with them, you have to keep adding them depending on how many like inlets, outlets you have. You need to add more of these transport terms. So when you put them together, you add them all, you get that summation, and you get V, which is your velocity times your area. And since density is, should be, have a, okay, so since density is like fixed at every point, I think we can make that assumption. Density is, it's incompressible. Make an assumption that the flow at section 2 is hours. Okay, so I guess we can take density as staying the same, and when you do that, your density term will actually just like cancel out. So now let's go ahead and solve this problem. So this problem is really easy. Velocity times area, we're gonna have V1, A1, this is actually a dot product, and if we do V1, A1 is gonna be your area vector, which is gonna be pointing out from your inlet or your outlet, right? So if we see here, they're actually opposite ways, which means that the dot product must be, there must be like a negative, since it's the angle is, what is it, pi. Since the angle is pi between these two, that means that cosine -1. So for V1, A1, we'll have negative V1, A1 plus, now these are all going in the same direction, so we'll have V2, A2 plus V3, A3. If you notice here, they give us a volume flow rate for 4. So how do we implement that into our equation? So velocity is really just length over time, or distance over time, and area times length, that gives us a volume, and volume over time, that's actually our volume flow rate, okay? So plus Q, we can nicely put Q in there. Now let's rearrange this to solve for our velocity at section 2. So 2, that's a full section. So I'm just outlining some keywords. Now if we go ahead and do the algebra to solve this for V2, okay, let's just go ahead and solve it, or set up the equation for it. V1, A1 minus V3, A3 minus Q, all of that over A2 is equal to V2. Okay, pretty simple stuff, just some basic manipulation, and let's just plug all our terms in. So doing all of this gives us -4.5. So if the assumption is incorrect, our final result will tell us. Now we have a negative. That means that that it's going in the opposite direction, right? If you remember from earlier how we got the negative here and we solved again, that means that this is actually not outwards, it's inward flow. Okay, next problem. We're given some equation here that will show us the velocity profile. And yeah, so let's go ahead and solve this problem. So we should have, so the fluid is going to be, so in our control volume, we'll have U here, the distribution along CD. So within the boundary layer along CD, so this is actually U over U. Okay, and we can just multiply this by to get to get this little u. This should be the boundary layer, the velocity distribution. Okay, and then because we have this like stuck to our plate, it adheres. There's nothing coming out through there, and I believe we'll also have fluid coming down like this. Okay, so now we're looking at our fluid flow, and let's just jump into it. Okay, yeah, let's just go into it and see what we can come up with. Okay, so let's see, what are we looking for here? Find the mass flow rate across surface BC. So BC, we need the mass flow rate. Okay, and now in order to find the mass flow rate, if you guys remember from last problem, we need to set up our we're gonna actually use this equation. So the mass flow rate across BC, this one, plus this has to be equal to our mass CD. Okay, now if we want to solve for MBC, CD plus AB. Alright, let's go into it. So mass of, we'll start with I made a really big mistake. This should actually be a minus. So let's start with AB. Okay, and then we need some sort of width. Okay, width. Okay, let's see really quick. Let me quickly just check something. With perpendicular. Okay, just making sure. So it's perpendicular. That means its width is going to be a 5 times 0.6, except 5 is in millimeters, so we need to convert that over to meters. So that's going to be 0.6 times 0.05. Okay, so let's plug in this right hand side really quickly. 1.24. Remember our velocity is going to be 30, and our area is composed of our width and our length. Okay, need to work on solving the first part. The first part is going to be okay. Okay, so we need to solve this. So when we take a look up here, we're gonna see that it tells us, so this area can be, so you see our y here, our y and our width, right? That's what composes our area. It's gonna be this y, and this width. So we can break the dA up into width times dy. Okay, and then we just need to find the bounds of dy. So dy, it actually gives us the bounds up here. Oh, oops. It gives us the bounds up here. 0, y is between those two values. And I'm gonna take, I'm just gonna worry about the integral right now, because that's gonna be the important thing right now. Density and our width can be taken out of this, and even this, the velocity, because we're gonna multiply that by this u over little u over big U. Okay, so this is our velocity distribution within the boundary layer, and so we're gonna plug this thing into our integral. There we go. Minus squared. Now we can break up this integral to two parts, right? Because it's subtracting. Take this 2 out, and I'm even gonna take this out because we're integrating with respect to dy. So y dy minus okay. And now let's just go ahead and solve these. So y squared over 2, you guys should know that, y squared over 2. 2 cancels out with this, plug that in, get squared. I don't know what sign that is, honestly. I think that's like a, okay, I don't know, whatever sign that is. Okay, I'm just gonna call it the duck. Okay, so now we have one of the ducks minus, and this is y cubed over 3. We plug in the duck, and we get minus the cube, the duck cubed over 3, and 2 that. So sorry, my work is a little messy, but trust the process, okay? So the duck minus the duck over 1/3, okay? So now we can multiply this duck by 3 over 3 and just subtract, and we'll get 2 of these ducks over 3, okay? Okay, and now we can plug in the value we know for that duck. Where is it? 5 or 0.005. So and you remember this u, we'll bring that down. It's gonna be 30. The width was 0.6, and the density 1.24. So now we need to add this, and we will get mass flow rate. I will do that calculation right now, or I will just use my calculator. Should actually be a negative sign here, and you should get 0.3. kilograms per second as your answer. Okay? Alright, and now on to the next one. We're gonna have a change in the density. So we're gonna be sort of uniform flow, which is in the tank, or uniform and time dependent. So we will unfortunately have to deal with this. So let's go set this up. Okay, so residual speed and density 6 through the area. Okay, so let's break this down to make this a little easier. So this right hand side, we know the velocity, the density, and the area. So this part is pretty easy. All we have to do is just plug in, and we need to change the units though. So I'm quickly just gonna calculate the changed units. Okay. Okay, and the volume, so this control volume, we can actually figure it out because they give us the volume here. So it's essentially just d over dt, and we're taking out the volume and we're just leaving in density. There we go. So now we can rearrange this equation so that this is density. So now all I simply did was rearrange this equation so that I have it in the differential form of density. I went ahead and computed it. Got 2.34. So this tells us that our density is decreasing as we leave the tank. Okay, so those were the 3 problems. I hope you guys learned something from how to use Reynolds Transport Theorem. So it's really dependent on what you're given in the problem. A lot of it is the setup. Okay, luckily for us, they did show us the setup. I wish I was able to set it up. I did a lot more just computing, but I hope you learned something. Thank you for watching the video.